So let's do vector addition and resolution and all that good stuff. Does that sound good?
Yes.
Do you have a problem you want to give me, or do you want me to make up one?
I'll give you one just because these worksheets, I probably wouldn't be able to do it myself, so we'll just do it that way.
Okay, perfect.
Okay. 2 Northeast Academy students pull on ropes attached horizontally to a box.
Okay, like here's the box, and here's one student pulling and another student pulling.
Okay. One student pulls with a force of 20 newtons at an angle of 55 degrees west of south.
Oh, okay. We're going to do the bird's eye view. You ready? So this is like north, west, east, and south. So that student is pulling which way?
That student pulls with west of south.
Okay, west of south. So let me show you west of south. When you do, how are you with west of south and east of north and all that jazz? Have you done that yet?
Yes, you look south and then go west.
Good. So west of south means you look south and then you go, was it 55 degrees?
Yes.
55 degrees west of south, right?
Yes.
And then this student's force is how much?
20 newtons.
20 newtons. Very good. Bird's eye view. Got it.
Got it. Okay. Next part is the second student pulls at 18 newtons at 15 degrees west of north.
Okay, west of north. So we're going to say take north and then go 15 degrees west of north. So there's 15.
Mm-hmm.
And this student, was it 18? How many newtons?
18 newtons.
Okay, great. So there we have 18 newtons. Now, I wrote it really high. Can you see that?
Yes.
Okay, so we've got 20 newtons and 18 newtons. Okay.
And then it says calculate the net force applied to the box. Show a vector addition diagram to support your answer.
I love it. Okay. So here's the foundation. In math, you can just add numbers like 18 and 20 and get an answer for 38, right?
Mm-hmm.
But because that's like when numbers are on a number line, and if you can picture the numbers both being positive, they're both headed in the same direction on the number line. They're either, and if something's negative, then it's headed the opposite direction. So you actually have to think about the direction of numbers being positive or negative. But in physics, when it's not just the positive and negative direction on the number line, but you actually have these other dimensions, north of west and east of south and all that stuff, you can't just add the 18 and the 20 because they're not headed in the same direction. So you have to actually, the only thing you can add is you can add east and west to each other, like positive and negatives, and you can add north and south to each other, north being positive direction and south being a negative direction. And then we're going to end up making a final triangle. So are you following so far? We're going to get a total on the east and west direction. We're going to get a total north and south. Are you ahead of me? Like, this is really easy.
Kind of. We didn't learn it that way.
Okay. Are you going to break down the 18 and the 20 into so let's break down, let's do this. Let's say on that 18, I'll just erase what I just wrote since it's not the way your teacher does it.
Okay.
So I'm going to do it the way your teacher does it. Okay. So your teacher, which one did he do first, the 20 or the 18, or what one do you want to do first?
We have not done this, but what he does is on the one before he talks about parallel something, so he drew another line and then he calls it R.
Oh, the resultant.
Yes. Yes,
the resultant. Okay, good. So the 20, can you see that the 20 is like a hypotenuse of this triangle?
Yes.
Okay. So if the 20 is the R, which is the resultant, and the resultant is usually on the hypotenuse, it's not always, but it usually is, can you see, all right, the resultant is, and I'll use the word resultant, but then I'm going to use my word that makes it easier, it's the shortcut.
Okay.
So if you are traveling, let's say you're going for a walk, and let's say you walked this far, like in the mall, you're walking down that hallway in the mall or that whatever, and then you walk this way. Do you agree that that purple pinkish line is the shortcut?
Yes.
Okay, good. So you can see that the resultant is the shortcut. You can also see that the resultant is usually the hypotenuse, but you could imagine that possibly you could have a triangle where if this is trip 1 and this is trip 2, that the resultant might not be the hypotenuse.
Yes.
The shortcut is not always the hypotenuse, okay?
Okay.
So, and I'm going to erase that. I just wanted to show it to you, but let's not have it be cluttering things up. All right, so what you want to do, the reason we want to break down the resultant, and by the way, these legs of the triangle, the legs are going to be the components. Has he used that word yet?
No.
The components are the parts. Like if you have the components to a stereo, it's just the parts of the stereo.
Okay.
Okay, so you've got component, let's call this like Y and X because of the direction they're going, okay? So these components, we're going to break down the shortcut into the two pieces. Now, math-wise, it's not going to make sense that the length of Y plus the length of X equals 20. That doesn't make sense because Y and X together are going to be longer than 20. However, from a geometry standpoint, Y plus X does equal 20 because 20 is the shortcut. So it's really weird. Yeah, you get it? So in terms of geometry, Y plus X does equal R because R is the shortcut.
Okay.
All right, good. So let's figure it out based on SOHCAHTOA trigonometry. So we've got this 55-degree angle in here, right?
Yes.
And with a 55-degree angle, we can figure out Y and X. Do you remember sine equals opposite over hypotenuse and all that good stuff? Great.
So you just do sine 55 times 20?
Yeah, exactly. So that would give us the opposite, which is X. So X is going to be sine of 55 times 20, which is the hypotenuse. So let's figure that one out.
I got 16.38.
Okay, perfect. So X is going to be 15.38.
16.
Oh, 16, thanks. Okay. So do you agree that that 16.38 is in the direction west?
Yes.
Okay, great. So we have to make sure we keep these directions straight because when you add a west direction to an east direction, your teacher's not going to tell you to make one of them negative, but it's just like on a number line. If you've got numbers going one way on the number line and numbers going the other way on the number line, you have to make one of them negative. It's not like you can add them together. So this one's going to actually be, we try to make west negative and east positive, just like the regular number line. We're going to make it negative 16.38 for X. Now this is when we add them together. Careful though. When you draw the vector, I'm going to say you either show the negative sign or you show the vector, which is like the arrow, but not both.
Okay.
Because the vector, the direction right here, this tells the direction.
Okay.
And whenever you have the vector on a triangle, when it tells the direction, it's redundant for you to also say negative. Therefore, you would never put a negative number on the triangle.
Okay.
So no negative numbers on the triangle sides because you already got the vector there.
Okay.
So the vector shows the direction. So you're going to have either a vector or a negative positive sign showing the direction. All right, back to our answer. We got X, and X is negative 16.38. Oh, by the way, it's newtons.
Okay.
Okay, so the units, by the way, when you do a triangle like this, you can't have newtons on one side and meters on another side. Later when you get into like a ramp and it's 100 meters tall and you're pulling something up a ramp with 50 newtons of force, you can't make a triangle and have the height of the ramp be in meters and the force of you pulling something up the ramp be in newtons. Every side of the triangle has to have the same units. So you can make a meter triangle or a newton triangle but not mix them.
Okay.
All right. We get on a lot of little tangents, but these little details help you later.
Okay.
All right. Let's go for Y. How can we solve for Y?
Pythagorean theorem.
Yes. You can do that, but you know what I like?
Mhm.
You can do that. I like to take the original given information, like the 20 and the 55, because whenever you use a rounded number, like the 16.38, to find your next number, every time you use a rounded number to get the next answer, you're a little bit off more and more. So if possible, go for the original information that was given because that's the most exact.
Okay.
So can we do maybe the 20 and the 55 again and use cosine?
Yes.
Okay, so let's do cosine of 55 times 20, and that's going to give us, and that's going to give us y.
I got 11.47.
Okay, thanks. So 11.7 newtons is y. Check it out. Is y going up or down?
Down.
Okay, so you can either draw the arrow, but what I like to do, because later we're going to add these things, let's go ahead and make it negative 11.47 newtons. And I know you know this, but up and right are both positive, and down and left are both negative. It doesn't have to be that way, but in general, most physics teachers and students decide to use those. It's like a convention that we decide on. We could do it the opposite way, but okay. So we'll make the down negative. And again, your teacher won't tell you to make it negative. They'll just try to test you to see if you know to make it negative because it's down.
Okay.
All right, we did one triangle. Now let's do the 18 Newton triangle. The one at the top. Because now we've got the x and the y. Here's the x, and here's the y, right? We've got those components. These are both of the components. We just found the two components, or the parts, of the 20 Newton force.
Okay.
Those are the two things we just found.
Yes.
But that's half of the problem. Now we've got to find the two components of the 18 Newton force.
Yes, okay.
I'm going to draw it over here. We'll say 18 newtons is the resultant. So now help me draw the two legs of the triangle that would make the 18 newtons the shortcut or the resultant.
So you just go...
You start from the beginning, and which way would I go?
So from the dot, go up north.
Good.
And then to the west.
Good. And you kind of just look at the picture and you decide where to stop to make it look like a right triangle.
Okay.
And you always want to use sine, cosine, and tangent, SOHCAHTOA, you have to always use right triangles because SOHCAHTOA doesn't work. They don't work on triangles that are not right triangles. So you have to make it, a 90-degree angle.
Okay.
So you just draw it and try to make it as close as possible. All right. Which one should we call X and which one should we call Y?
X is the horizontal one and Y is the vertical.
Okay, good. All right, can you help me solve? Oh, what was this angle, 15?
Yes. Okay, so you do sine 15 times 18.
Perfect.
And that is 4.66.
Good. And which side did we just solve for, X or Y?
X.
Good. And so you got X is what, 4.66?
Yes, but then it would be negative.
I like it. I like it. Way to go.
Okay, and then Y would be cosine. 15
Yep. Times 18. What'd you get?
17.39.
Okay, 17.39 newtons. And is that up or down?
Down, so it's negative.
Check it out. Look at the drawing.
Oh, it's up.
Yep. So we'll
Positive.
go up. So we'll say Y is positive 17.39 newtons. Okay, we just got the two components of the 18 newtons. So we're making good progress.
Yay.
Okay, to get the final answer, and by the way, your teacher might give you 4 different students pulling in 4 different directions. Luckily, he only gave you 2.
Okay.
But you could do this 6 times if you had to, if you had 6 students pulling on this box. You could do it as many times as you need to. But what you're going to do in the end is you are going to get your total horizontal, and you're going to get your total vertical force, your total horizontal force and your total vertical force.
Okay.
And then we're going to make what I call a final triangle with the totals. So let's add up the total x's. So total horizontal will be our total x.
So that's negative 4.66 plus negative 16.38.
Yes.
That is negative 21.04.
Okay, newtons. Now, you see why the negative matters? Because, by the way, if we hadn't put those negatives on there and we made it positive, we might think that our total x is going to the right, because we could maybe add them and say, oh, it's 21.04, so we would end up drawing it, to the right, blah, blah, blah. No, it's not to the right. It's a negative number, so it's going to end up being 21.04 going to the left.
Okay.
Okay, that's why the negatives matter in the middle of the problem. Okay, let's get our total vertical.
So 17.39 plus negative 11.47. 5.92.
Okay, so it turned out positive?
Yeah.
Good. So that one's going to be, the x is going to be left and the y is going to be up. And I put the positive and the up, which you're not supposed to do. So watch this. I'm going to erase the negative and erase the positive because we're about to do them in a triangle. So we've got the 21.04 left and we've got the 5.92 going up. Or I should say west instead of left because this is north, south, east, and west. So do you agree we've got our totals?
Yes.
And now we don't need anything of the past calculations because we've got our totals. Now let's do, in the bottom left, I'm going to erase the mess that's right here. And we're going to do our final triangle so that I don't have to turn the page.
Okay.
All right. So in the final triangle, let's do the x is going left, right?
Yeah.
So it doesn't matter if you draw the x or the y first. But notice that we draw the vector, so we go 21.04 newtons. Okay, that's our total x.
Okay.
Now, when you draw the total y, every student is tempted to go like this for the y. Because doesn't that look kind of cool?
Mhm.
But that's not what you do when you add them. You don't start again at the same place. What you're going to do is you're going to say wherever the first force ended, that's where your second force begins.
Okay.
Is y going up or down? Ooh, it's going up, isn't it?
Yes.
Okay, excuse me while I change everything because I need space for it to go up.
Okay.
That was not good planning. All right. So we have 21.04 newtons going to the left. And then the y goes up. And how much does the y go up?
5.92.
Okay, I totally did not draw this to scale. Because shouldn't the 5.92 be much shorter?
Yes, but it's okay.
It's okay. You don't mind. Okay.
No.
All right. So I am also going to try to make this one a little bit longer. Oops. That is really wrong. There we go. Okay, so next. You've got your two components. You've got your total x and your total y. Remember, don't put the negative sign on the x when it's on the triangle. And now we're going to draw our resultant, which is our final answer. How should I draw the resultant, which is the shortcut?
Like from the end point of 5.92 and the starting point of 21.04?
Yes. Do you want me to go from there to there?
Yes.
Okay. That is what everybody does at first because it feels good. It feels really good to make the arrow go back home, right?
Yeah.
But is that black arrow the shortcut of the two pink arrows, or is it taking it back home? Is it really the shortcut of what the two red arrows were doing?
No.
It's the opposite, isn't it?
Yes.
What should I do instead to make it the true shortcut?
Change it to going towards the destination.
Exactly. The shortcut has to go from the beginning to the end.
Okay.
Now we can use Pythagorean theorem. Because
Okay.
there's no other way for us to get this, right? And by the way, we don't know the angle yet, but that's okay.
Okay.
So we do a squared plus b squared equals c squared.
Okay, so you okay. 21.89.
Okay, great. How come I got 21.856? Did you do 5.92 and 21.04?
Yeah. Oops. No, wait, I got 21.856.
Okay, great. I did too. Okay, so 21.856 or 857, and we'll round it in a second when we figure out our significant figures. Okay, so that's our resultant. What about the significant figures? Look at the original numbers. Everything had 2 sig figs, right? The 18 and the 15 and the 55. Did
Yes.
the 20 have a decimal place after it? I hope.
No.
Shoot, it didn't have a decimal point after it.
No, it didn't.
Well, I'm going to pretend that he meant to put a decimal point after it. Here's why. If he did put a decimal point after it like that, like this 20 right here with a decimal point, that has 2 significant digits. If he didn't put the decimal point, it only has 1.
Okay.
So the thing I don't like about 1 significant digit is teachers don't usually do 1 because then you're going to round your answer to like 1. You're going to round your answer to 20.
Yeah, he usually doesn't make a big deal out of sig figs.
Okay, good. If he doesn't make a big deal, then he forgot to put the decimal or something like that. So let's say R equals let's give 22 because 21.85 rounds. Let's at least do 2 significant figures since most of his numbers were 2. Does that sound good?
Yes.
I mean, I'm tempted to go 21.86 because it sounds better.
Mm-hmm.
But 2 sig figs is really what we're limited to. I mean, you could show both answers.
Okay.
All right, we're almost done. It feels like we're done because we got an answer and we circled our answer and it feels great and we did so much work. But why are we not done yet?
Because you need the angle.
Perfect. So we need to figure out this baby right here. And you always get the angle of where the resultant is coming from. You don't do that one. You don't do where it's coming to. You always do where the resultant's coming from. All right, so help me do it.
Okay, so we can do opposite over this, and so you do the inverse of tan.
Very nice. Yeah.
5.92 divided by 21.04.
Yeah, I'm just making room up at the top here. And let's do that in a nice deep blue color that I like. All right. So you said inverse tan of theta, whatever theta is, right? Or no, tangent of theta, excuse me. Tangent of theta is opposite over adjacent, 5.92 over 21.04, right?
Yes.
Which means inverse tangent. You're ahead of me, I know.
Okay.
Inverse tangent of 5.92 over 21.04 equals theta.
Okay, and for that I got 15.71.
15.71. Oops. So then let's do 16 maybe? What do you think of 16?
Yeah, that's good.
So 16 degrees is our angle. All right, now it also feels like we're done because we got the angle. But here's what teachers love to see. When you give your final answer for all of these types of problems, they want to hear you say it. Do you remember in the original problem they said a student pushes or pulls with 18 newtons at 15 degrees west of north?
Yes.
You have to phrase the answer like that. So you're going to say the resultant is 22 newtons at 16 degrees, and then you're going to have to say west of north or east of south or whatever it is. So let's do that. Let's say R equals 22 newtons at 16 degrees. And now look at the bottom triangle here, way down here, our final triangle.
Mhm.
Is that north of east, or what is that?
West of north.
Yeah, did we go from north to west? Like, look at the top right here. West of north means you start at north and you go west. Did we start at north and go west?
No.
We started at west, and see how we started at west and we went north?
Yeah.
Because out of these two, out of the black and the pink, which one is like the north, south, east, west vector?
The bottom one is the west.
Yeah.
So, like, the black line is your vector.
Exactly. So the bottom one is the west, so we went north of west or north from west.
Okay.
If we had gone west of north, it would be an angle like from here to here. It would have been, this would be west of north.
Okay.
Do you see that? So this is west of north. But the one that we've got here, that theta, that is north of west, which simply means that we went north from west.
Okay.
So in your final answer, at the very top in the middle of the page, we'll go 22 newtons at 16 degrees north of west. And that is the complete answer that your teacher will love and give you full credit for.
Okay. Okay.
So it's a lot of work. It takes like so much room, right?
Yes. It's just tedious. I feel like it's easy to make careless errors, too.
I know, but you won't. But the thing is, in the middle of all this, every time you get part of the answer, it feels like you're done because, like, you do a lot of work and then you get an answer like the X and the Y and you get the R. And it so many times in the middle of the problem, it feels like you're done. And then you're like, oh, my gosh, I'm not done yet. Right?
Yeah.
So you just have to keep going until you get the angle and the direction, and you can, like, put it into a little phrase, like 22 degrees at 16 degrees north or west, and then you're done.
Okay.
Good.
Okay, there's one more.
Got it.
Okay. This one, there's a big graph on it.
Okay, let's draw a big graph. Let me do that. Like this. Do you see that?
Yes.
Okay. What are there points different places or arrows, vectors?
No, it's just like a grid. It looks like grid paper. I think it's only like the quadrant 1, so it would all be.
Oh, okay. Let me undo that.
Mm.
Like this. With
Yes.
grid paper. Okay, good.
I think so.
I'll pretend it's grid paper. We'll do it.
Okay. It says a plane takes off from an airport on a heading of 30 degrees north of west and travels for 100 miles.
Got it?
Okay. It then turns to a heading of due south for a distance of 200 miles.
Okay, due south for 200 miles. Okay.
It then turns and heads 20 degrees east of north for 300 miles and lands.
Gotcha.
Calculate the net displacement of the plane.
Okay, great. So it doesn't even tell you how fast it's going. This is all distances. All of these babies are distances.
Okay.
So when they say net displacement, they're just saying how far it went.
Okay.
So you can do this graph like 30 degrees north of west for 100 miles. Does he want you to use a protractor, or should we do angles based on rise over run?
He wants us to use a protractor.
Okay. So do you have one with you or not?
Yes.
Okay. So I'll do it approximate and you can do it exact. But let's do for 100 miles and 200 miles and 300 miles. Do you want to use like 1 centimeter is 10 miles?
Sure. Yeah.
Is there enough room to do that?
Yes.
Really? Like, all right, 300 miles would be 30 centimeters. That's pretty far. That's pretty big. 30 centimeters is like as long as 3 cigarettes. Do you have...
Oh, no. Let's not do that.
There's not do that. Okay.
We could do like an inch is 100 miles.
Yeah. Or an inch is 50 miles because that'll make it a little bit bigger.
Okay, let's
Or wait.
go 50.
No, you're right, because 300 miles would be 3 inches, and that's probably big enough, right?
Yeah, that works.
Okay, good. So we'll do an inch is 100 miles. All right. So I'm going to estimate, I'm going to start here, and I'm going to estimate 100 miles at 30 degrees. And it's north of west. I was so tempted to go like this, but what is this angle? Is that north of west?
No, that's east.
Is it north of east or east of north?
East. You look east, go north.
That's north of east. He's trying to trick you because he gave you a grid that's the first quadrant, but north of west is, you're going to have to go into the second quadrant.
Okay.
So we're going to, not that he's trying to trick you, it's just we can't use the first quadrant for north of west.
Okay.
I mean, he would never try to trick you, right?
Mm.
We hope not.
Yeah.
All right. So I think that's good enough erasing. So I'm just going to start with a point. And let's see, I'm going to predict where this airplane's headed. North of west, south, east of north. Okay. So I think you should start down, kind of down. Well,
okay.
Maybe like there, because you're end up going to go south, but you're going to keep going. We'll try it. We'll see. East of north. Maybe I'll start in the middle. Okay. So let's go 30 degrees north of west. So here's west. I'm going to go 30 degrees north of west. Did you do something like that?
Yes.
All right, and that's going to be 100.
So you started in like the middle?
Yeah, is that okay? Where did you start?
I get confused. I always have to redo it.
Me too. I just had to redo it like twice. You're not,
Okay.
That's totally normal.
Okay, so...
Because you don't know where this thing is going.
West of north. Let's see.
Yeah, north of west is going to be...
30 degrees.
Mm-hmm. North of west.
Yes,
So
I got something like that.
Something like that. Okay, now we're going to go 200 miles due south, which is nice and easy. So let's go like twice as far due south. That's supposed to be twice as far.
Okay.
So do 2 inches down.
Okay.
Is that good?
Yes.
Now we got to go east of north. So when I do east of north, I got to say, okay, this is north, and this is east of north. I have to sort of picture it in my head. So I'm going to head east of north at 20 degrees and go 300 miles. So this airplane is very confused. Right? But east of north is in this little spot right there.
Okay, so let me see. Let's see. For 300.
Yeah.
Okay.
Luckily, on your graph paper, you'll probably, if you do the protractor, you'll probably be able to just draw the shortcut, the resultant, and you'll be able to measure it and see how far it went.
Okay.
Without doing like a million calculations. So if you do your angles with the protractor and you're really careful about the inches and the angles, you probably can measure the resultant.
Okay.
I'm going to do the resultant in green. Tell me when you're ready to draw the resultant.
Okay, hold on. I'm doing my 3 inches.
Okay.
Okay. Okay, I'm ready.
All right, where should the resultant start?
Let's see. I guess at this.
Remember, it's a shortcut, So you want to go from the very, very beginning to the very, very end.
So from your starting point?
Yep, which is at the beginning of the 100. So that should where the resultant should start there, and where should the resultant end?
At the end of 300.
Yep. So it's going to go like this, and yours is probably more accurate than mine in terms of angles.
Yeah, mine looks different.
Does yours look, well, good, because yours is probably correct. But does yours look like the resultant is on top of the 300 or not?
Yeah, it looks like it's just like bigger. It's a bigger thing.
Okay, no problem. Yeah, because my lengths and everything are just estimated. All right, so now measure, if you would, measure the length of your resultant.
Okay. I got 3 inches, so 300 miles.
For your resultant, really?
Yes.
I don't think that could be right, and let me tell you why. Because your
Uh-oh.
resultant, I don't think, would go... Did your 200 go straight down?
It went, oh, you know what I did?
What?
I drew my 200 from my starting point.
That's what everybody tries to do at first. So you have to draw the 200 where the 100 ended.
Yeah. Okay, hang on. I'm erasing it.
Okay. Everybody wants to do that because it feels better to do everything from the same starting point.
So you go down 2 inches. Okay, and then you go...
So wherever the second vector ends is where the third vector starts.
Okay. So you... okay. So for 20 degrees east of north, you look north, go east.
20 degrees. Say that again. 20 degrees east or north. You look north and go east. Yes.
Okay. So look north, go east. Mine's still different, though.
Okay. Tell me how yours looks different.
It's,
Did you do, you know what? Tell me what to do and I'll do exactly what you're doing. Did you do 100 like that?
yes.
Then what did you do?
I went down from 100 to 200 meters.
Okay, straight down?
Miles, yes.
Okay, so straight down like this. So that's 200, but you probably went longer. Okay.
Yes. And then from the end point of 200, I measured out 20 degrees and went 300, but it's like a long line, like, and not close to the 100.
Really?
Yeah.
Did it cross through the middle of the 100?
No.
It went far. So did you do 20 degrees from here? Like, is that your 20 in there?
No, I did it from...
Did you do it from
like
the horizontal?
Flat part.
From the horizontal?
So was I supposed to do the 20 degrees from the 200?
Yeah, I'll tell you why. Do you see how it says east of north up here?
Yes.
Okay. So the east of north means from north go east, and that's your 20.
So from north.
So that's why the 20 is going to be in here. Now, if you did your 20 here, if that was your 20, what would that angle be? What would that be in terms of north, south, east, and west?
North of east?
Exactly. This one right here is north of east. If he had said north of east, that would be where you draw your 20.
Okay.
But since he said east of north, you got to do the 20 inside here.
Okay, I get it.
Do you get it?
Yes. So now my like 300 miles goes through the 100.
Good. Does it go actually through it or at the end point of it?
Through it.
Okay. So it's like it crosses?
Mhm.
Okay, no problem. So we'll have it cross a little bit, like it kind of went like that, I guess. Let's see. So you have your 300 here.
Mhm.
So are you saying that your resultant, hang on, let me move the 300. Are you saying that your resultant is going to end up like from the beginning to the end like this?
Yes.
Okay, that's okay. That's approximately, I mean, that's possible for sure.
Okay.
And this one is your 300.
Mhm.
All right, now you're in good shape because that's reasonable. So now you can measure the length of the R.
Okay.
And
Let's see. I got like 1 1/4 to like 125 miles.
okay, 125 miles. We like that. And I think he wants you to give the direction. Now you've got a choice on the direction. You can choose, it's going to be the same exact answer. You can choose to go, I'm going to draw your resultant off to the side here for a second. Okay, there's your 125, right?
Mhm.
Okay, you can choose to either do this angle, which is east of north,
Okay.
in your answer, or you could measure this angle and report it as north of east. So it doesn't matter because it's the same answer as long as, but there's going to be two different numbers, but you could measure the east of north angle or you could measure the north of east angle. Together they would add up to 90, and you could report either one of them and you'd still be right.
Okay.
So which one do you want to measure?
East of north.
Okay, so you're going to go for this one in here. You're going to use your protractor.
Hang on.
Okay.
Okay, so my resultant is almost like a straight line though.
Good. It should be. Actually, mine is curved, but it shouldn't be. So let me redo mine. Like I just was doing it too fast. It's supposed to be a straight line.
Okay, but it's not like at that much slant. It looks like it's almost going completely like straight up.
Vertical? No
Yeah.
problem. I just draw my angles approximate, but if you've got a protractor, you're saying that this angle is really small. Like in other words, if this is north, you're saying that your resultant is like really close.
Yes.
Okay, no problem.
So like me. Okay.
What'd you get?
It's like a really small. Let me see. So I look north, go east.
Mhm. So it's really small, like 1 degree.
It's like maybe 2.
Okay, good. That's not, yeah. You know, when he has you do your protractor and you're using inches to measure, everybody's answer is going to be a tiny bit different, and he's going to not be that because it's not like you calculated it, so he's going to be a little lenient on this kind.
Okay.
So we know it's according to your measurements 125 miles, and then remember you're going to say at, and then you're going to give the angle.
Okay. So like 3 degrees.
3 degrees, and then what do you say after that?
East of north.
Perfect. There you go.
Okay. And is there any way to actually like figure out the length of your resultant without your protractor?
Yes. You could do what we did last time. You see how we did it this time when we broke it down into the X and the Y's, and then we added up our X's and we added up our Y's?
Yes.
We can do that. If we wanted to, we could break up the 100. Now the 200 we don't have to break up because the 200 is just in the Y direction.
Okay.
So the 200 is 100% Y and the 0 in the X direction.
Okay.
But we could have broken up the 100 into a triangle. So we could have begun like, okay, 100 this way, and we could have said 30 degrees is in here.
Okay.
You know, and we could have done a triangle. I know I'm being messy here. But we could have done a triangle with 30 degrees, and we could have figured out our x and our y. And then on the 300, we could have made a big triangle on the 300. And we could have gone like, okay, 300, and we know that it's 20 degrees this way, so we could have done a big triangle with the 300, and we could have gotten the x and the y on the 300. You see that? And then we could have added up all of our x's and all of our y's to get a total x and a total y. And then we could have, after we got the total x and the total y, we could have made a final triangle. And remember that the second, this 200 right here, the y would be 200, actually negative 200 miles because it's down. It's negative. I keep wanting to get the bright red and I keep missing it. So y equals negative 200 miles. And in this one, with the 200 going south, the x is 0 miles. Because for that one, it was 200 straight down, so there wasn't any x direction at all.
Okay.
So you could have added up all the x's and all the y's, and you could have gotten a total, and then you could have made a final triangle.
Okay. And then, let's see. So then you just figure out the negatives again by, like, get the direction of your arrows?
Yep. If it's left, you make it negative, and if it's down, you make it negative.
Okay.
Yep. And so he wanted you to do it both ways. He wanted you to do it with the total x and the total y, making sure you did negatives and positives correctly. And then he wanted you to do it measuring with your protractor and your ruler.
Okay. Got it. But, like, would the answers still be, like, around the same if I were to go through all the triangles and do that?
You know, if you do it this way with the x's and the y's, you get the most accurate answer.
Okay.
So you could do it that way and compare to see how your measurements were with your protractor, see how good you were.
Okay. Well, that's all the problems he had given us. We did one in class.
Oh, really? So do you feel good about these?
I think I just need practice at this point, I think.
Yep. Do you want me to give you one made-up problem for practice?
Sure.
The one thing I want you to remember is, the one thing that you learned was, do you remember on this one with the airplane? At the end of, when you were doing the 200, by accident you started your 200 at the very beginning, at the beginning of the 100.
Okay.
So make sure you always start vector 2 at wherever vector 1 ends, that's where you start vector 2.
Okay.
Yeah. Okay, so I'll make up another one really quick. All right. So, a boy and a girl. The girl is going to be really strong. A boy and a girl are pulling. Oh my gosh, do you want me to give you a really hard one?
Sure.
Really? He's going to give you, all right, he's going to give you one like this.
Okay.
Hang on, let me just think if I'm going to give you this really hard one. Have you done weight yet, like converting mass to weight?
No.
Okay. I'm going to go ahead and introduce you to the concept of weight. Okay. So, these are two cables, and we're holding up the Mona Lisa.
Okay.
There she is. All right, so the Mona Lisa is being hung in a museum. All right. The Mona Lisa weighs, how much does the Mona Lisa weigh? Let's say 140 newtons. I have no idea, but let's just say she weighs 140 newtons. Now, weight is a force that's down.
Okay.
Okay. I'm going to say that each one of these cables takes half of her weight. Okay? So we're going to split her weight between these two cables. So two cables, and each takes half her weight. Okay. Now, all I have to give you is the angle of the cables. Let's say that they are at 40 degrees each. I'll make it easy and make the angles the same, but he'll give you one with different angles. We'll get to that later.
Okay.
All right? So 40 degrees each, and each one takes half her weight. So the question, what is the tension? And tension is a physics word. I'll tell you what it means. What is the tension on each cable? Tension just means the force pulling on each cable. So when I say the tension, I'm just going to say it's the force on each cable holding up the Mona Lisa. And usually tension is the force in a rope or a cable that's just supporting something.
Okay.
All right? So what I want you to do when you're doing this one is to imagine both of these cables as parts of a right triangle. You good with that?
Mhm.
So we have these right triangles. As a matter of fact, let me undo that really quick because I think it would be easier to picture if we did the right triangles this way.
Okay.
Okay?
Mhm.
So we've got two right triangles. Do you agree that if each cable is taking half of the weight, that each cable is vertically, because weight is vertical, it always goes straight down, so you're going to get good practice all year long whenever you draw your weight. And weight, he might draw weight as FG, that's one syllable, one symbol for weight, or some teachers do W and some teachers use MG. But these are all abbreviations for weight, so you'll just see which one your teacher uses, okay?
Okay.
So I'm going to use FG. That's probably most common. It's the force of gravity. That's FG, is force of gravity.
Okay.
So the force of gravity is 140 down, right? Do you agree that each cable vertically is supporting 70 newtons?
Yes.
Okay, so here's what we do. We go 70 newtons on this vertical and 70 newtons on that vertical. Because
Okay.
when you're supporting weight, you're supporting it vertically. You can't, the cables are supporting it at an angle, but because the 140 newtons is down, you have to put 70 and 70 on the vertical parts of these triangles.
Okay, that makes sense.
Okay, good. So we've got 70 newtons going up on this cable and 70 newtons going up on this cable. So now we've got two triangles that are pretty easy because now, check it out, here's a triangle. We know that this is 40 degrees, and we know that there's 70 newtons up on this.
Mhm.
Do you agree that the cable is pulling up and over?
Yes.
So it's like the direction is up and over. And so the resultant, the way the cable is pulling is up and over like this.
Okay.
So can you use trigonometry to figure out the tension on the cable? So the tension is just the force on the cable.
Yes.
All right, let's do it.
Sine 40 equals 70 over x.
Yeah, good.
So then you do
Sine 48 maybe over 70 equals x now. Is that right?
and then you do 70 divided by sine 40, I think.
Except
Yeah.
that'll leave your hypotenuse in the denominator. Let's write it out. Because if you do sine of 40 equals 70 over hypotenuse.
Yeah.
Let's call it T for tension, okay?
Mhm.
I think we need to switch. Maybe this is what you said, but T then equals 70 over sine 40.
Yes, that's what I did.
Okay, good.
And then I got 108.90.
Good. And that makes sense. because it's more than 70, because the hypotenuse is longer than the leg.
Mhm.
And so 108.90 makes sense geometrically. So the tension in each cable, since the angles are the same, the tension in that cable is 108.90. And that's your answer. Now, if he asked you for the tension, you just have to give the tension. Since he already gave you the angle, it's not like he's asking you for the angle of this cable.
Okay.
He gave it to you.
Okay.
But do you see how that works, where you're supporting the Mona Lisa?
Yes, I understand it.
Good. And the weight is a force that goes down. It's a force of gravity pulling down on an object.
Yes.
And you split it between the two cables. By the way, can you imagine that these two cables, because they're both pulling up and out, right? So you've got, I'll try something in like bright yellow if I can find a bright yellow. I don't know if this will work. Let's try this. Okay. So this cable's pulling this way, and this cable's pulling this way.
Yes.
Okay, that's kind of orange. So because the cables are both pulling up and out, the force, the tension horizontally on cable A and the tension horizontally on cable B, that actually causes the Mona Lisa not to move right or left, because the tension on cable A equals the tension on cable B. They're like pulling equally. It's like a tug of war, and they're just holding her steady.
Okay.
And also the vertical, because she's not moving up or down, the vertical 70 plus 70 is equal to the vertical 140 down. And so everything is in equilibrium, which is a word for equal forces going up and down and equal forces going left and right, and she's not accelerating. She's not falling.
Okay.
All right. You got it.
Got it.
Okay, let me